In this next laboratory, we're going to be looking at a first set of experiments where we'll use a LabVIEW for controlling data acquisition. And in addition, we're going to go ahead and introduce the first laboratory setup, the compound pendulum, because it has a pretty straightforward sensor installed, and this allows you to focus primarily in this first week on learning how to build a LabVIEW virtual instrument that can control the MyDAC device and collect signals from the setup. And in the following lab, then you'll actually do some modeling and experimentation with this pendulum setup. For now, in this quick lecture, I'm just going to review some basic sensor concepts using the compound pendulum as an example. The compound pendulum setup is a pretty straightforward device. It has, as you can see here, a rigid aluminum pendulum that's connected at its base there rigidly to a stainless steel shaft that sits on two bearings. The end of that shaft goes into a potentiometer that's used to measure the angular position as the pendulum oscillates about this angle, right? So I mean it's theta, so it's obviously going to oscillate about this vertical equilibrium here. So say plus and minus theta. And usually we'll clamp this breadboard to the table here so the base doesn't move. And there's a simple wire that's connected to your MyDAC. So here you'll see a simple schematic for what a rotational pendulum looks like. It's got three terminals. There's the shaft of your potentiometer, as you may know, rides on a slider here, and so you're basically forming a resistor, right, between each of these terminals. So for example, between terminal 2 and 3, right, you're forming a resistor, say here to there, and another resistor here to there. So you can see how the two resistors vary, and what you do then is connect these three terminals to power, ground, and then we'll usually pick off the signal from the middle terminal there. We'll look at this circuit in the next slide. The potentiometer is one of a large class of modern sensors that are mostly electromechanical. And we like electromechanical sensors, right? Because if you think of a sensor as just a system, you put power into it. Typically, not all sensors need power, but a lot of sensors need power. Then there's some ideal signal variable of some type that affects that sensor, and then we get some electrical quantity that changes, right? And often what we want to measure is something easy like voltage, say. But the quantity that might be changing, like in the case of the potentiometer, is resistance, which is why we often need for many of the sensors, including those shown here, some kind of signal conditioning. We like to classify sensors according to these, maybe at least these 3 or 4 different types, but in particular pay attention to the fact that most sensors are resistive, capacitive, or inductive, which means they're sensors that depending on what physical quantity you're trying to measure, they cause changes in, say, in the resistive sensor, there's changes in resistance that you can then detect, obviously in capacitive sensors and inductive sensors. The parameters that change then for those types of sensors are either capacitance or inductance, and so you build circuits around the sensor so that you can detect those resistive changes, usually converting those parameter changes into some kind of voltage. Another class of sensor is a piezoelectric, which we may talk about later when we introduce accelerometers and other kinds of sensors. But this image here just shows a few different types of these sensors: resistive, capacitive, inductive, and piezoelectric. The basic physics of most resistive sensors is pretty straightforward. They're easy, usually low cost. Remember that resistive sensors rely on a change in resistance that can be detected in order to infer some change in some kind of physical parameter. We can use a really simple case of a uniform conductor. If you recall from your physics class or electric circuits class, that resistance, say for a uniform conductor here that has some uniform area, rho is resistivity of the material, then you have a length. Then the resistance, then you can say, oh, hey, that resistance depends on rho, and then the ratio, say, of L to A. Sometimes you can conceptually think of all electrical type parameters this way as being, and really all physical parameters as being formed by a set of quantities, one being the material here, a material quantity, and this is a geometry. So if you think about it, if you can take advantage of changes is in either material or geometry, then you can form a sensor because it'll cause a change in resistance, and then all you need is a circuit that can pick up that change in resistance, and then you can measure any of these quantities, right? Either length, area, or resistivity. And that's basically what I'm saying there. Often you can measure resistance directly just by using an ohm meter, but most of the time we'll use some kind of a signal conditioning circuit so that we can actually infer resistance change from a voltage. And that's much easier for us to measure, say, using an analog to digital converter that measures voltage on something like the MIDAC that we're using in this lab. And most modern day microprocessors, for example, have A to D converters that you can easily measure voltages from. So that's why we often want to dress our sensors up with a signal conditioning circuit that provides that kind of functional change. So being a little bit more explicit about that, a signal conditioning circuit can convert an electrical parameter change, in this case a resistance, into an easily measured voltage change. So if you recall here's a simple voltage divider circuit. We might put some voltage here. This doesn't have to be Vn. This could be a power supply voltage, say +5. If you have a resistance and you can form a simple voltage divider, and then you can measure the voltage right between those, and from the V out, knowing V in, and you can then basically infer that there's a change in one of these quantities. And if you think about the basic potentiometer, right, that had slider, and remember you basically had two resistors here. So if you can form a circuit, a voltage divider circuit on these three terminals, you have, say, R1 here, R2. R1 and R2 are both changing, so you can then infer from the voltage that comes out of this other terminal that you're changing, for example, this length. And then you can, in a sense, calibrate for the position of this. Remember, the shaft is connected onto this little slider. You can then measure angle, for example. They also make, by the way, linear potentiometers, so you don't have to have rotational potentiometers. You can buy, there are a lot of potentiometers you'll see that are little boxes, and as this guy moves in and out, effectively in here you have just a linear potentiometer this way, and wherever this slider touches, you've got, again, two resistors in here, right? And again, you'd have the three terminals. So you can also find many linear potentiometers that are available for measuring linear, translational motion as well as rotational motion. Now our interest is in calibrating. Here's a little drawing of a rotational potentiometer. You have a mechanical input here, you have terminals. So basically you have a little circuit here where, say, you don't have to put plus and minus 5. One nice thing about putting bipolar connections here is that then this output here, if it's properly centered, will be right at 0. So for example, when your potentiometer is perfectly centered, you'll have a 0 for 0 volts for 0 displacement, right? So Actually, if you look at this calibration, what this does is it says whatever voltage that I measure tells me what angle I have, right? So this is the basic idea behind a calibration. Is you might put your potentiometer at a different angle, measure the output voltage, and if it's linear as shown here, you can then basically find that slope. That's what you'll be doing in the lab. By the way, a lot of times you'll make these measurements and you'll find, oh, that guy's not going through zero. You know, the points might have a non-zero here, and you can get the y-intercept here. A lot of times the reason that happens is because the you know, if you think about that, let's say in the case of the pendulum, the shaft might not be centered, and you could loosen that. We ask that you not do that. The TA could do that for you. You could center the potentiometer so that when it's sitting straight down, the actual potentiometer is, you know, zeroed. But don't worry about this non-zero y-intercept. These potentiometers should be linear over the range that we're using them. By the way, there are some potentiometers, angular potentiometers, that maybe aren't made for, don't have what's called a linear taper. They could have, if they're made for audio applications, you might see a potentiometer that has an audio taper, and those may not be linear. You might have a nonlinear curve here because they're not necessarily made for measurement. They're made for adjusting a resistance for some kind of tuning circuit. So be careful to look, if you're buying one, a linear versus audio taper in your potentiometers, because then you won't have a linear trend as shown here, right? The goal of a calibration then is to get this function that you can then use by then what you have translated the whole measurement into detecting voltage and getting output position measurement from your sensor. Now, a note about why we like to build linear sensors is if you have a linear sensor, then it says, without reading all this, is basically it says, hey, if I look at a signal, let's say I look at a voltage signal, you know, coming out of the MIDAC and say being plotted in LabVIEW, if you say get the voltage out over time, if you have a linear relationship between the say the position and the voltage out of that potentiometer, then when you look at signals like this, you can sort of assume that trend is following the actual relationship. Otherwise, if you could have a nonlinear relationship that relates the quantity of interest, say position, to the voltage of your sensor. If it's nonlinear, then you need a nonlinear function to correct for that. If it's linear, then you can actually just look at that signal, and it's just a simple calibration constant that you need. So, for example, this would just be in, say, the units of this calibration constant would be something like radians over volts, right? So you multiply it by the volts that you measured, say using your DAC unit, and the output then is in radians, and you've got a measured output. Okay. Again, nowadays with computer-based instrumentation, having a nonlinear resistor, a nonlinear sensor is not really a big deal, because you can always put a function in there that makes this correction for you, right? So that's why it's important to run calibrations that show you how your quantity of interest, say here position, is related to the output voltage. And that's something that you will do in the lab.